Between 1645 and 1715, the Sun underwent a transformation that baffled astronomers. For 70 straight years, the dark magnetic patches on its surface sunspots virtually disappeared. Across Europe and North America, temperatures dropped so low the era became known as the Little Ice Age. The River Thames in London froze thick enough to host months-long festivals on the ice, while shortened growing seasons led to widespread crop failure and famine. This wasn't a collection of random bad winters. Historical records from the 17th century show a massive, measurable void in the Sun's normal one-year cycle. Where thousands of sunspots should have appeared, observers counted fewer than 50. Data from ancient tree rings and ice cores shows this pattern repeating across 1,000 years. The Sporer, Maunder, and Dalton minimums each align with centuries of shorter growing seasons and agricultural stress. In 2019, the Sun entered its quietest phase in over a century. For 281 days out of the year, nearly 80% of the time, the solar surface was completely blank. This downward trend tracks the Sun's magnetic activity over the last 4 decades. Every consecutive solar maximum has been weaker than the one before it, leading to the exceptionally deep minimum we saw in 2019. If the Sun's magnetic engine is slowing down to levels not seen since the 1700s, it raises a question for our own survival. Are we entering a second Little Ice Age? Despite the historical record, a new solar minimum will not trigger a global freeze. Our atmosphere operates under a very different set of physics today. NASA climate models show that a Maunder minimum level drop in solar output would cool the planet by about 0.3 degrees Celsius. That is a small fraction of the 3 to 5 degrees of warming projected from modern greenhouse gas emissions. Sunspots act as magnetic pressure valves for the Sun's algae. They are regions of intensely concentrated magnetic fields that suppress the flow of heat, appearing dark only because they are slightly cooler than the 10,000-degree surface around them. A quiet sun won't stop global warming, but the reduction in its magnetic output changes how our weather systems move and distribute heat. The most immediate impact of a quiet sun is found in the jet stream, the high-altitude river of wind that bottles up freezing polar air at the top of the globe. Normally, a strong jet stream forms a tight barrier around the North Pole, but when solar activity drops, that barrier weakens. It begins to wobble and sag southward in deep vertical waves. Those sagging waves act like giant scoops, pulling Arctic air far south of its normal boundary. This traps extreme cold over specific localized regions for days or weeks at a time. We saw the result in February 2021. Sub-zero temperatures plunged into Texas, causing $200 billion in damage and leaving millions without power as the grid collapsed under the cold. These atmospheric shifts turn a predictable solar cycle into a series of localized, systemic shocks to the infrastructure we rely on. The Sun's influence reaches well beyond the clouds. At the very edge of space, reduced solar energy changes the physical footprint of the planet itself. A drop in ultraviolet radiation causes the upper atmosphere, the thermosphere, to begin cooling and contracting inward toward the Earth. This contraction removes the atmospheric friction, or drag, that usually slows down objects in low Earth orbit. Without that drag to pull them down to burn up, satellites and defunct rocket stages stay in orbit significantly longer. This leads to the Kessler threat, an exponential increase in cascading collisions. In a quiet solar environment, the debris field in our orbit multiplies, threatening the satellites that power our global financial systems and internet. A quiet sun exposes a hidden vulnerability in the orbital infrastructure that our modern digital civilization depends on. There is one benefit to this silence. A quiet sun produces far fewer of the massive solar flares that create these auroras. Fewer solar flares mean fewer geomagnetic storms hitting our power grids, sparing our transformers from the kind of surges that could cause catastrophic, long-term blackouts. Today we have spacecraft like the Parker Solar Probe diving into the sun's outer atmosphere. We are no longer passive observers. We are actively monitoring the sun's poles to forecast these exact risks. The sun's rhythms are ancient, but our vulnerabilities are new. We have traded the agricultural risks of the 17th century for the technological risks of the space age, and our survival now depends on how well we listen to the silence of our star.